Hello, everyone. My name is Brad Holden. I'm resident here at UC Santa Cruz at UCO Lick Observatory. Not actually at UC Santa Cruz, but technically at UCO Lick Observatory. I'm going to talk today about work I've been doing with Garth Illingworth for a long time now, more time than I care to think about, along with Arjen van der Velde, Dan Kelson of Carnegie, Marian Franks, and a little bit with Shannon Patel. What I'm going to talk about are scaling relations and size evolution amongst early type galaxies. So when I talk about early type, I mean galaxies with very low star formation rates, passively evolving systems, quiescent galaxies, boring galaxies like this. They're very smooth, essentially concentrated. You can characterize them pretty well with a handful of parameters. And so that's why I kind of like to study them, because their structural properties are easy to understand. We don't have to worry about quantifying clumps and arms and bars, because they're relatively smooth stellar systems, and we can understand them with a handful of kinematic measurements, such as velocity dispersion, or maybe velocity dispersion and rotation, and their stellar populations are also relatively easy to understand, though this talk will be surprisingly stellar population free. And we find these systems even at relatively high redshift. Here's some early work at redshift 2. When I say early, because it happened in the last decade, 2008, and it used NICMOS. This isn't in WFC3IR, though these little tiny postage stamps up here are Keck AO images, which was kind of fun. It's only an hour on a 10 meter. And you can see once again that they're relatively smooth stellar systems. But the key result of this original work by this work by Peter van Duckum was that they're much more compact stellar systems at high redshift. So they've undergone some sort of structural changes over, early type galaxies have undergone structural changes over the last 10 or so gigayears. And so I'm going to talk today about the evidence for that and what we think we can learn about what mechanism causes that structural changes from the data. And when I talk about scaling relations, I'm going to be specifically talking about these classical scaling relations. And this is called the fundamental plane. The usual line from Dan Kelson is, it's not fundamental and it's not a plane. It is a projection of the virial theorem. And so you can derive almost the coefficients in front of the three variables here. This is the velocity dispersion. This is how fast the stars are moving within the galaxy. This is the size of that stellar distribution. And then this is simply the surface brightness. This is, in effect, a measurement of the mass to light ratio of the stars in the stellar system. You can kind of derive the coefficients if you just make the assumption that the stars have roughly the same mass to light ratio and use the virial theorem. You get almost the way there, but you don't actually get the correct results of the slope. But nonetheless, it tells you that from a structural point of view, early type systems are relatively easy to understand because they all lie in this sort of relatively simple manifold. The diagonal lines are simply divisions based on how bright or faint the galaxies are, and that goes into this next plot where these are the same three bins that were shown in the previous plot. But this is the face-on projection of the fundamental plane. So I'm now taking, or in this case, Jenny Graves has taken the fundamental plane and sort of rotated it so you're staring at it face-on. And the reason why to do this is that the structural parameters now are the key things to look at. The x-axis is the velocity dispersion, how fast the stars are moving around inside the galactic potential, and the y-axis is the size of the galaxy. And you can see that, relatively speaking, in this low redshift Sloan Digital Sky Survey based sample, the early type systems kind of uniformly occupy this plane. I mean, there are parts of the parameter space that they don't occupy, and then there's parts of the parameter space that are not occupied because of selection issues. But up here and down here, there's not very many galaxies. But there is generally a relatively uniform distribution throughout this part of parameter space. And so we can then use these sorts of measurements, sizes and velocity dispersions, and study these galaxies at higher redshift in this same sort of projection. And changes in the population tell us something about how galaxies are evolving with time. So Arjen van der Velde took a bunch of data. Some of it was from work that Garth had done with Peter van Duckum and Marian Frank. Some of it was his thesis data, and some of it was Tommaso Treo's data. And once again, this is last decade. And he found something very interesting, or we found something very interesting, which is that this plane is no longer uniformly occupied. At a redshift of 1, early type galaxies are smaller at a fixed velocity dispersion than they are today. That where galaxies populate in this face-on projection of the fundamental plane is different. If you look at these lines here, those are lines of roughly constant dynamical mass. If you take the velocity dispersion, you square it, you multiply by the radius, and you pick some coefficient like 5 in front, you get in the right units, you get solar masses. And so what this plot is over here is simply this plot here projected along the lines of constant mass here. And this makes the difference pretty striking and lets you measure that, say, at 10 to the 11 solar masses, galaxies at a redshift of 1, early type galaxies at a redshift of 1, are roughly a factor of 2 smaller. So we have evolution that goes like 1 over 1 plus z. I actually had people ask, are you sure you did your cosmology correctly? Because there's angular size diameter versus the other distances. But this is what you get. You get galaxies, even at modest redshifts, low redshift, I believe, was what was used in some of the earlier talks today. At the low redshift of 1, only 9 or 10 gigayears ago, in look-back time, early type systems were actually more compact at a fixed velocity dispersion. And you can even move, even though no one in this room was involved in this paper, but out of fairness, I'm going to reference this. There's been efforts working to even higher redshifts, and here's a work at 1.6 using the LRIS spectrograph on Keck. And once again, they find the same kind of thing, that there are galaxies that are highly compact, less than a kiloparsec in half light radius. Think about that. Half the stars are within less than a kiloparsec, and has a velocity dispersion of like 280 kilometers per second. It's an extremely compact early type system. So these exist. And the nice thing is that no longer are we using stellar masses to find these things. We're actually using velocity dispersion. So they're dynamical measurements. We know we can rely on the mass measurements. So this summary also motivates this. So we have now an observed evolution. And this is Casey's recent work on the candles data. And he puts the field evolution here in the sort of gray. And it says 1 over 1 plus z. And what's particularly interesting about this paper is that what question you would naturally ask is, how do you make systems grow in radius? You have these early type galaxies. They have velocities that are very large, 300, Peter van Duckum's 500 kilometer per second system, for example. And they're very compact. And they have to get bigger with time. And so you can, theorists, of course, are smart. That's why they're theorists. And they have come up with a variety of mechanisms, probably more mechanisms. One is not necessarily orthogonal to the other, right? There's no. So thanks, you completely derailed my train of thought. So there are a variety of mechanisms that people have proposed to explain the evolution and make galaxies bigger over time. One of which is minor major mergers, one of which is major mergers. Also, people promote mass loss, that in effect galaxies somehow lose mass and thus stay at the same size and just become smaller. And then there's the adiabatic expansion, which strikes me as an explanation in search of a physical mechanism, but maybe I just don't understand it. But the key thing is that the nice thing is that if mergers are a mechanism that cause galaxies to change in size over time, then the observed evolution should depend something on the merger rate. And what Casey is showing here is that cluster galaxies, as denoted by these particular points, seem to evolve slower than field galaxies. So that would say that somehow a galaxy at a fixed velocity dispersion knows what larger dark matter halo it lives in when it grows in size. So cluster galaxies get bigger, field galaxies get bigger, but field galaxies get bigger at a more rapid rate over time. So this raises the question of, well, in the local universe, are field galaxies and cluster galaxies, do they have the same size-mass relationship or not? If they don't at high redshift, why would you expect them to at low redshift? So this is a complicated plot, and I'm probably going to spend my next 10 minutes trying to explain this, but bear with me, please. So this is the velocity dispersion size plot again for a Sloan Digital Sky Survey sample. This is the same plot I showed you before. These are lines of constant mass, the dotted and dashed lines. This blue straight line is simply the median size at a given velocity dispersion. And so you can see that it's sort of, galaxies get bigger as you go to higher mass. Bigger galaxies are bigger. Oh, great discovery. And then the dashed lines on either side are the 25th and 75th percentiles of the distribution. So the smallest 25 percentile galaxies at a given dispersion live here, and the biggest 75 percentile live up here. The first thing your eye is going to pick up is that there's this turn up over here that is completely that's not physical. That is simply a selection effect from doing magnitude limited surveys. So pay no attention to that. So over here, this is a field galaxy sample from something called the NOAO Fundamental Plane Survey. It's targeted looking at nearby clusters of galaxies. They publish all their velocity dispersions. They do not publish any sizes. The sizes, therefore, also come from the Sloan Digital Sky Survey. These galaxies in this survey are also present in this survey. In some cases, they also have the same velocity dispersion measurements. So, and I have a boring plot that shows you they get the same measurements. What you see here in orange is the size dispersion relation for the cluster sample. It's not the same. It's statistically significant at like the 5 sigma level or something like that. So in the local universe, at a given velocity dispersion, cluster galaxies are smaller than field galaxies. Is it a lot smaller? No, it's a few percent. It's not a huge effect. But even in the local universe, cluster and field early type systems have different size distributions at the same velocity dispersion. So now let's go back and look at velocity dispersions of cluster galaxies at higher redshift. Because Casey showed evidence that there's a potential for the pace of size evolution to be different. And so here we have that same NOAO fundamental plane sample here with the weird orange lines that denote the median 75 and 25 percentiles of the distributions. And the red dots are cluster galaxies at a redshift of 0.8, roughly half a Hubble time ago, so 7 or so gigayears ago. And you can see that at a given velocity dispersion, they're all smaller than today's cluster galaxies. So yes, cluster galaxies today are smaller than field galaxies at the same dispersion, but there's still significant evolution in the distribution of sizes at a fixed velocity dispersion for cluster galaxies. Charlie? Right. That could be one solution. My knee-jerk is that it's the morphology density relation, that you're not actually picking exactly the same galaxies in the field because the spiral fraction is, or early type spiral fraction is going to be higher. If you look at the distribution of spiral galaxies in the field, the size mass distribution, they're always bigger than early types. And so it's my knee-jerk. But the question you're asking can easily be checked. I went and re-reduced a whole bunch of Sloan imaging to do exactly this kind of thing. And that was fun. So I can actually make these plots. Right, so there is size evolution in cluster galaxies. Now remember I said it's roughly a factor of 2 for redshift 1 field galaxies and redshift 0 field galaxies. Here you can see that it is probably not a factor of 2. It is slower, as Casey earlier proposed. And so we can make the same plot that Casey made before, where here's the 1 over 1 plus z evolution that Casey was showing before for reference. And here are 3 data points that are based on velocity dispersion measurements and size measurements, either from the Sloan, thank you, or HST imaging. And you can see that the pace of the evolution is much smaller, that in agreement with what Casey showed, that the sizes of cluster galaxies grow over time, but they grow at a rate that is slower than the rate that people observe for field galaxies. And these black points out here are based on stellar masses. They're not based on velocity dispersions. So part of the reason they have large error bars is that, and part of the reason why they have large error bars is because they're small sample sizes. But they sort of agree with the trend. So this is Casey's data point right here. And there's a data point at a redshift 1.3 cluster by Alessandro there. So I'm probably going to be one of the few people that goes under time so far. In summary, at a fixed dispersion or stellar mass, passively evolving galaxies in the past are smaller. I think I've said that about 10 times today, so I don't need to probably say that anymore. And that there does seem to be a difference between the size distribution of cluster galaxies versus field galaxies. I don't know why. I don't know if that's truly a physical effect. Gets back to Charlie's question. Is this truly a physical effect, or is this some sort of difference in the selection? But it's tantalizingly interesting. More importantly, I think the pace of evolution of early type galaxies in clusters is slower than the pace of evolution of early type galaxies in the field. And that, I think, points to the idea that merging is an important part of the size growth we see. And because merging is rarer in clusters, we see a slower pace of evolution. Because the encounter velocities are high, so the merging rate is low. The encounter velocities are 1,000 kilometers per second. No, the densities are not big enough.
It's the merging of galaxies in
Clusters, not the merging of clusters themselves. Any other questions? Ben? I would imagine that tidal effects would be the dominant reason for size growth both in clusters and in groups. And how the difference between that and merging I've never been very clear on. It could be that they're effectively two completely different processes, or they could be sort of related. I'm not sure. But certainly. Yeah. Yes. Yeah, if you want to do this quantitatively, you're going to have to include both of these effects. You're going to have to predict, based on your model, what you think the growth is for a given physical mechanism. And at the same time, yes, the cluster population is going to grow by a factor of 2, roughly, in number between 0.8 and today. So therefore, all those new galaxies, as you say, are recently quenched. They have a different size, progenitor size distribution. Right. Yeah.
You also could check if more extended galaxies are slightly bluer and younger still.
Oh, yeah. The age. I'm glad you asked that question, and I'm bummed I didn't bring my plot. And I can show you tantalizing hints that amongst massive, passively evolving systems, at high redshift, they're less round. Yes. Yeah.
So, and would you argue that people who call size evolution, galaxy, actually not dissecting properly because it could be a galaxy at redshift 2 that's actually across today, while lower redshift is actually possibly not equal to the environment?
Yeah, I think that is, worrying about the progenitors, I think, is going to be a key part of trying to understand all this, yes. And I suspect, yeah, if I were to ask Peter, for example, what the halos, the typical halo that a 10 to the 11 solar mass galaxy lives in at redshift of 2, what halo it is today, he would probably tell me it's a 10 to the 14 solar mass system. And so, yeah, it could be that all of these things at Z of 2 are actually cluster galaxies in the making.
One more thing regarding mergers and clusters. The high redshift clusters on the sun,
No, the velocity dispersions in high redshift clusters are high. There's 600, 700 kilometers per second. So it's, well, 1.6. I need to give this to Charlie.
Thank you. Can I borrow my laptop? Yes, your laptop, please. Can I borrow the pointer?
This is not mine.
Very fast. That's too high.